All right, looks like we're live. CNBT 1311. This is chapter 4, which will being week 3 and 4. And we're going to start with floor systems. And most of this is structural engineering. But you need to pay attention to it as an architectural designer because you have to work with your structural engineer and you need to decide what kind of system that you're going to use. It's just like doing the site plan, the foundation plan. This is another piece of the giant Lego set of building a functional structure that's economical and hopefully will last. All right, so let's start with floor systems. All right, the bottom line is if it's a slab on grade, as we talked about before, then that is your floor system. It's supported by the earth and the sub-earth underneath it. They're horizontal planes that must support both live loads, which are the people, furnishings, and the movable equipment. And if it's a commercial building, depending on what activity's in there. The dead loads is the weight of the structure, the weight of the carpet. If somebody wants freaking marble up here, then all that has to go into account. If it's an elevated floor, like this joist floor here, and you're going to put a ceiling covering over this, that weight has to go into it. Anything that's attached to this. Now, what about this giant bookshelf over here? All right, Mama wants to come in and move this thing over here. And so now the weight's been redistributed, hopefully to a load-bearing structure. They can be composed of anything, a flat plate, beams of wood, steel, or concrete, and all kinds of manner of beams, which we will get into at a later date. Not only does it have to support the moving loads, it also needs to have minimal deflection. I mean, nobody wants to have a second floor or a third floor that is like a trampoline. Everything has a deflection. So its floor system has to be stiff enough to reduce the bounce. Okay? All right? The bouncing. In lightweight commercial construction where they're using lightweight bar joist, that sometimes is a problem. You'll walk across these floors and you'll feel a slight bounce. Well, that's because they didn't take consideration the stiffness of what's holding up the floor. Another thing is sound attenuation. If this is the second floor and this is the first floor down here, well, everybody's lived in an apartment, I'm sure, that these people up here are noisy as all get out, or these people down here are noisy as all get out. They jumping up and down on the floor. All right, the depth of the floor construction is something you got to worry about and consider. This is an open web bar joist. I love these things because you can run mechanical stuff through here, like your plumbing and your sewage and your HVAC system, and you can hang a suspended ceiling underneath here for fire retardants. But whatever your floor system is, you got to worry about fire. In residential, they'll put gypsum or sheetrock under here. I hate sheetrock, but that's just my opinion. Stuff's left over from World War II, and we hadn't broke our addiction to it. Of course, I don't know that there's a better product out there other than that right now for quick, cheap ceiling or wall covering that can be repaired easily. All right, he makes a comment here. Except for exterior decks, floor systems are not normally exposed to weather. Well, not normally. Your mileage is going to vary. Trust me, it's going to vary. Honestly, down here. Let's start with concrete. Your major floor systems are concrete, steel, and wood. Not too many self-supporting floors are made out of masonry. Cast-in-place concrete floor slabs are classified according to their span, and we'll get into that in a little bit on the next page or so. Precast concrete planks that are set across your beam structure, now those are one-way slabs. They're one-way slabs. I'm a big proponent for two-way slabs. You can use a lot less concrete, span more of a distance, and control the wind resistance of your building if you use a cast-in-place two-way slab. I'm a big proponent for two-way systems. Steel beams, they support your decking. And they can be supported, the beams can be supported on all kinds of stuff. It can be an open web bar joist, and the decking is a part of that. And you can weld that decking to the bar joist and create a giant diaphragm up here, just like this would be a cast-in-place diaphragm. There are all kinds of systems. The problem with precast panels going across a steel structure, it's very hard to make this into a diaphragm and be economical. Let's see, what else we have? He makes a point here of joists have limited overhang potential. Well, that's true, and that's not true. I've used heavy, they're not bar joists, these are bar joists because the web are little bars, and the bottom card and top card are angle iron. But I've used heavy steel joists that are all angle iron, top and bottom. These are angled. These are heavy structural members in here. Okay, and I've supported them with an overhang on both sides. Now, what does this look like? Well, in just this two-dimensional drawing, going this direction, okay. But what if we had interlaced heavy steel joists going that direction? Then it's starting to look like a space frame, right? Okay. All right. Again, your mileage is going to vary depending on the economics. And we want to make our structures as light as possible, but we want to keep the deflection down. You get too light and too long of a span, this is going to bounce. All right. Of course, we've talked about the benefit of a diaphragm for shear, for wind loading, in the previous videos. Wood beams. Okay, there's a lot of wood framed apartment complexes, and they can be supported on girders or posts or load-bearing walls. Concentrated loads and floor openings may require additional framing. Well, no kidding. If I could cut a hole in this, whether it's wood, steel, or concrete, I've got to have additional framing around here to support that opening. And we are going to have openings. You have to have openings in your floor system for stairs, elevator chases. Of course, we've already talked about the elevator columns being a shear column, are like the pagoda pole, right? Going up through the high-rise building. All right. Relatively small, closely spaced joists may be supported by beams. We've already talked about that. Subflooring. That's the underlayment. Now, if this is plywood, we can make this plywood subfloor a diaphragm if we glue and closely screw or do engineering nailing. You and your structural engineer will have to have that conversation. If you don't approach this as a diaphragm, then you're really missing an opportunity to stiffen up your structure and make it lighter. All you got to do is support the weight of the construction loads up here, and you might have to put jacks underneath there and jack beams while you're laying the deck down, gluing it and screwing it, or using ring shank nails to create this diaphragm until the glue cures, and then you can remove the jacks underneath it, and it'll support more of a load. This is he's talking about support structural planking. Now this is just like tongue and groove flooring, um, and you can treat this as a diaphragm, but there's a lot more nailing involved, a lot more gluing, and I would suggest you also use a good glue like liquid nails in your design because it'll keep the bounce out. Because we all know this wood is not uniform. But as you're laying your floor, your decking down, you got to watch the deflection of the construction load, all those people up there and equipment and all that stuff. So you may have to do some kind of sub-jacking underneath until you get it all done, and then you yank the jacking out. All right, we'll see some examples of that a little bit. Okay, concrete beams, reinforced concrete beams. Now he gives you some rules of thumb. Okay, here he says you want a clearance of 1.5 inches minimum cover to protect the steel reinforcement for fire and corrosion. Now this is exposed to either the interior of a building. This is not concrete on grade. Concrete on grade, like the footings in the previous videos, we said needed a minimum of 3 inches of cover. Wastewater treatment systems, we want 3 to 4 inches of cover. And because we're also going to water coat some kind of coating barrier on the clarifier walls and the sludge digester walls that are made out of reinforced concrete. All right, but for general structural concrete that's not exposed to the ground, you want at least 1.5 inches. And you designers don't forget that 3/4 inch bevel. If not, that's going to look like nasty stuff. You want that bevel. And what they do, they'll come in here with the form, and they'll have a bevel strip, a wooden bevel strip, and all this gets sprayed with release agent, form release agent. Then they'll lay that steel cage in there for the beam, and they'll have to have rebar chairs in here. Most of them are plastic now. All right. He gives you some other rules of thumb in here. Now remember, a rule of thumb is not gospel. This is not written down on a stone tablet, handed down by God from Mount Ararat. Okay. Rule of thumb is a general design idea that, let's say you're an architect and you say, okay, I want my span of my concrete, depth of concrete beam is the span divided by 16. Okay, so theoretically, if you've got a span between your architectural elements in your building and you're sketching it up on your butter paper and say, okay, I can get by with a ratio of my span over 16. All right. And it's in 2-inch increments. Don't do something funky like 1 3/4 increments. Just stay in 2-inch increments. All right. The code for this is the American Concrete Institute, ACI. ACI, American Concrete Institute. Long time ago in a galaxy far, far away, I was on a couple of ACI committees as a structural engineer. All right. Your effective depth, now this is for structural engineers, because you as an architect don't care about that. Your structural engineer does. It's from the top of the cast in place concrete to the center of the lower reinforcing steel. Now, there's no extra charge for that. Now, your beam width, it should be equal to or greater than the width of the supporting column. Now, whenever possible, this is very important to your designers. As designers, okay, whenever possible, you want to vary the required steel reinforcement rather than the beam size, okay? So you come up with your ideal beam size based on the span, and the structural engineer's he does all his loading, and and does his calculation and says, yeah, okay, we'll use some heavier reinforcement in here without increasing the size of the beam. Because what happens if you increase the size of the beam? Remember, concrete weighs 150 pounds a cubic foot? Well, if I can get by with an 18-inch deep concrete beam, but because I want to save on rebar and I have to go with a 30-inch concrete beam, I've just increased the weight of my structure for no reason at all, for no good reason. But you don't want so much reinforcement in here that you can't get the concrete around it, because that's what makes this stuff work. You've got to have the coarse aggregate and all the aggregate when they run that vibrator spud down in here when they're casting it to vibrate and get a good dense feel. You want this really dense, and that's why they vibrate it. With those spud vibrators, while they're casting this, because you want that concrete and that aggregate to get all around that rebar so you can have good adhesion. Because that way to act as a unitized device. This doesn't have much to do with you architects, okay? But it's a good idea. It's a good representation, I mean, of the problems we get into as structural engineers, all right, and contractors, for some of you who may go into construction management. How are we going to get all this extra reinforcing steel at this rigid joint? Remember, this is a rigid cast-in-place joint, all right? How are we going to get all that concrete around that reinforcing steel? Some designers will put so much reinforcing steel in there, you can't get the concrete around it. We got to back up. All right. Let's see here. Bottom bars are longitudinal bars. Okay, most of your heavy reinforcement in a beam like this, because remember, in the other chapter, the beam's going to do this. Okay. All right. What are we saying here? Diagonal tension results from the principal tensile stresses acting at an angle to the longitudinal axis of the beam. Now, I know that just tickles you to no end. All right. I don't know why Ching put that in there, but it doesn't matter. That's why we have these vertical hoops or stirrups. Okay. All right. Act as two things. It takes care of some of the longitudinal cracking. Now, if you're in a high-rise building and you get to look up the concrete beams and you see a beam with these longitudinal crackings like this, or diagonal, I mean, you need to run. You need to run, call somebody. Bad things are happening in here. Bad things. All right. This is, I don't know why. Anyway, all right, if you're a rebar layer, an iron worker, hooks or bends given to the end of the tension bars to develop an equivalent embedment length, okay? What he means by embedment length is the amount of the longitudinal length of the reinforcing steel that's in this concrete, okay? Now, there are some discussions in ACI committees on, does this really help? And it does, okay? Because what actually gives you your strength in your concrete is your embedment length. So if I had a block of reinforced concrete and I just stuck a single rebar, I'd have to stick it way down in there, okay? But if I put a hook on that rebar, and formed it like that, then I wouldn't have to stick it down so deep. What he's talking about. Concrete slabs. Concrete slabs or plate structures are floors that are reinforced to span either one or both direction. One-way slabs or two-way slabs. And which is my favorite system? You in the front row on that third seat. Oh, that's right. It's an online class. You know I like two-way slabs, but we'll talk about the one-way slab first. Sometimes you can't get around it. If you've got a rectilinear building, it looks like a shoebox, then yeah, you're going to end up with a one-way slab. It's going to be going back and forth like this. Now, certain aspect ratios, what I mean by aspect ratio is the narrow side versus the long side. At some point, you get away from a two-way slab and you got to go with a one-way slab. All right. It's not necessarily bad. I mean, you're not going to go to architectural hell if you have to do a one-way slab. You and your structural engineer work this out. But this is all cast in place. See, this diagram is representing cast in place. Okay. Now, Ching gives you another rule of thumb over here. These are rules of thumb on these spans. Everything in this book is a rule of thumb. I've told you before, if you go design something and don't get your engineer, and y'all do the calculations and you use these rules of thumb, don't be surprised if you go to court in a lawsuit. So, all right. In the best projects, the architect comes up with the grand scheme and immediately gets with a structural engineer, a good one, and they start working together. I've sat down elbow to elbow with architects in my career, and we'd make changes and this and no, dude, you can't do that. I mean, this is concrete. It's not unobtainium. We don't have an unlimited supply of unobtainium that can span thousands of feet with nothing to support it. All right, hadn't been invented yet. So we got to come up with some unique ideas. Okay, why not stick a reinforcing wall, a load-bearing wall out, and then instead of it being a flat concrete wall, use architectural forms to make a pattern. All right, a one-way slab. Okay, now this is a one-way slab. Now it's all cast in place, and this is a pan system. This is a tapered pan. It goes up underneath the form system. This stuff's all jacked up, and it creates a void underneath here where you need it, just like this. And what does this do for us? It lightens up the total structure. Instead of having this big, thick, super slab, right? And it makes it cheaper. You're using less concrete. And you can control your stresses, where the loads are going. You and your architect will get together. Two-way slab and beam are just a two-way flat slab. All right? That means that it's a certain aspect ratio, mostly square, and you can start distributing the stresses in two directions and balance that stuff out. And balance it out. Portland Cement Association and the ACI got together many years ago and created a manual for two-way slabs. So what you do is you just split your grid system up into more of a square, all right, for the bays, and you can use less concrete. And you don't have to necessarily put a bunch of beams across here like you had to up here, all right. Again, your mileage is going to vary. You get with your engineer and y'all work this out. And on a two-way slab, like a waffle slab, we'll get to that in a second. All right, what's his rules of thumb up here? When spanning square or nearly square, that's right. And can carry intermediate to heavy loads over 15 to 40 feet. Again, you get with your engineer, all right? I've had some two-way slabs in some wastewater treatment plants, the dewatering buildings that were 30-foot squares and holding up some heavy centrifuges, dewatering centrifuges, to sling the water out of the sewage sludge before the sludge went into the dryers. All right, two-way waffle slab. Why don't we call it a waffle slab? Because it looks like a waffle, right? Now, just like this up here, where, oh my God, this is why I don't do cooking shows. There we go. All right, just like this is sort of like a void, right, in here. All right, it lightens it up. Well, look at this. This is a two-way waffle slab. So if we've got this long span, okay, and here's some rules of thumb over here. But again, I wouldn't stake my life on these rules of thumb. All right, we've gone to 24 feet to 54 feet, okay, with possible of post-tensioning We'll get into post-tensioning in a little bit. Again, for maximum efficiency, they need to be square or nearly square as possible. All right, because the more linear you get from your width, your narrow, as the longer side gets longer and the narrow side gets narrower, it becomes a one-way system, and it's hard to get this stuff to flow in two directions. Well, we've lightened up this with a waffle slab, and we'll talk about this later, but you can see these solid reinforced pads here are for punch and shear, to keep the columns from punching through the slab. All right, two-way flat plate is nothing but a solid piece of concrete over columns. I'm not a real good advocate for this because this really makes me not sleep at night. And they look cool because the bottom slab is clean, right? But, and again, there's some rules of slab over here, but you really got to watch your punch and shear. That's a structural engineering thing. What you see on a lot of these two-way flat slabs is just what we found in the waffle slab up here. For greater shear strength and moment resisting capacity, remember this is going to act as a diaphragm. The bending stresses are going to come around through here and come back down into the column. Same over here, okay? You can reinforce these shear pads, cast them in place with the slab, do a little drop down on top of the column, and reinforce this. Reinforcing detail would look something like that. There'd be some more reinforcement across here in reality, and there'd be some temperature steel down in here, because this is all going to be in shear. It's going to try to punch a hole like a paper punch right through that slab. And again, the rule of thumb of the angle is anywhere from 30 to 60 degrees. We used 45 as an average and never had a problem. All right. Suitable for relatively heavy loads and spans from 20 feet. Again, there's another rule of thumb. And you can see how the shear stresses from the capital. Here's an architectural term. Column capital. You can Google Greek columns and you can look at the capitals they put on the Parthenon, the top of the columns, but this is called a capital. It's a bell-bottom footing upside down, right? So, of course, it's going to be a nicer looking bell-bottom footing because you're going to form this, okay? Make the architects happy. And now these capitals can be square or they can be round. All right, pre-stressed concrete. How are we doing on time? We're at 28 minutes. Yeah, these videos are like dry, right? They get dry like watching paint dry. All right, pre-stressed. That means that the steel, the reinforcing steel, for a lack of a better word, is stressed before the concrete's poured, okay? So we're pre-tensioning it. I've got some videos that I am going to put on D2L. I've already got them pulled off how this stuff works, post-tensioning and pre-tensioning. There's pluses and minuses for all this stuff, okay? Pre-stressed concrete are like those concrete panels that we talked about setting across your floor joist, all right, your floor beams, all right? So you put a high tensile stress on this, then you cast the concrete, and then you cut these loose, and the beam bends. It bends up. It puts a chamfer in it. We call this a camphor. I'm sorry, not a chamfer, a camphor. So it's bent up a little bit so that when you load it, it deflects back down to a predetermined, pre-engineered level once it's loaded, okay? So it's preloading it. It's like making a spring, a leaf spring on a car, all right? But it's out of concrete. And this is called pre-tensioning. I expect y'all to read all this. I'm not going to read this to you. Um, all right. And you can ignore this down here unless you want to be a structural engineer. Okay. Um, but this is how it works. Okay. You got your dead load stresses plus your pre-stress stresses equals the combined dead load and pre-stress stresses. Okay. So there's a certain amount of initial pre-stress is lost due to the combined effects of elastic compression or creep of the concrete. Doesn't that sound cool? Um, and these tendons, when they're cut, yeah, they do shrink in there a little bit, but hey. Now, pre-stressed concrete. The extremely high strength stress tendons may be in a form of wire cables. Okay, and this is all post-tensioning. Okay, now we're in post-tensioning. What do you think post-tensioning is? That's after the fact. Post-tensioning is the pre-stressing of a concrete member by tensioning the reinforcement after the concrete is set. We're really not pre-stressing. I don't know why he stuck that in there. Post-tensioning is after. This stuff is not under tension yet. All right. And if you watch those videos, you'll see how these tendons are laid specifically over the high stress areas and the less stress areas, so that when it is stretched after the concrete's poured. So now the concrete's poured. Then we come in here on the ends, and those videos have a very good detail of those dogs on the end here. Okay. Then they're securely anchored to the jacking end, and the jacks are removed after the post-tensioning process. All right. Now, some of these tendons can be left unbonded. Some of them are in a sleeve. Okay. And it depends. The unbonded ones need to have grout injected in them to keep them from moving over the life cycle of the structure. But that's all in those videos. All right. And this is a whole, pre-stressing and post-tensioning is a whole different school of engineering. I am not a big fan of post-tension slabs, especially for residences down here, because it all depends on how good that construction crew is. Now, commercial post-tensioning, where you have a set of specs and an inspector that's supposed to be paid to watch what the contractor's doing, and testing labs and that sort of thing to watch the pressure gauge and monitor what's happening to the concrete deflection-wise is one thing, but we know that does not happen in residential construction. You got a lot of chucks in a truck doing this. All right, and no matter how good the company has a track record of, it still boils down to how good is your construction crew. How well did they set these on the form? In the form. And watch those videos I put on D2L. When I get them up there, I'll give you a notice. I've already pulled them and cataloged them, but I hadn't put them on D2L yet. You will see an email. All right. Load balancing is the concept of pre-stressing concrete. You want to balance your load. All right. There's a good lecture by a pre-stressing and post-stressing geek in those videos on D2L. Now, again, you're not designing this. You are not doing the engineering calculations. Yes, you're going to end up taking statics if you're going to be an architectural student. Why? I have no idea, but it's a part of your pathway. All right. But you are not going to be doing these engineering calculations. Trust me. All right. He talks about the parabolic trajectory. I'm sure that just excites you. Let's see. Yeah. So you drape them, and then you pull them, and it pulls the beam up, and it puts stress in the beam to support load. All right. Here's cast in place concrete floor. This would be like on a second or third floor. This could be the ground foundation, or it could be the second, third, fourth, fifth, sixth, all the way up floor. Okay. Now, He says these are proprietary systems, and I guess they could be proprietary. They've been around for 1,000,000 years. Um, there are farm companies that will subcontract with your contractor, and they'll get with the engineers, and they'll have all kinds of conversations that the architect is like, okay, just make this happen. Because the engineer is the one that has to put his stamp on the structural stuff. If it falls down and goes boom, then he's the one that goes to court, maybe goes to jail or whatever. All right. Now, we know that concrete is liquid stone. That's what I call it. It's it's formable. That's why we call these forms. You come in here with these jacks, and you jack all this up. There's a whole group of people called construction engineers that before any of the steel gets laid, these forms are checked for level and alignment and all kinds of stuff. And then they sign off on it, and then your iron workers come in here and you put the reinforcing steel in here. Okay, or you come in here, and if you're going to use these pan forms go in first, and then the iron comes in, and then after that, all that's checked and inspected, and then you're cleared to pour the slab. All right. Let's see. This is a flying form. You'll see this on a lot of high-rise jobs where they use the same form, or actually they use several, because let's just say we're going to pour. This is the foundation. Okay, remember the columns going down under the earth, and there's a drill footing. Okay, so this is all earth down here. Here's your columns. Okay, all right. Well, your flying forms come in here, and here's your column base. So there may be one flying form on this side, and then there'll be another one over here, and they're picked up with a crane, and they're ferreted in and set up. And so this flying form will stay down here until this concrete reaches a minimum strength. Now, once this concrete reaches a minimum strength, enough for construction on top, they'll take another set of these and then slide them in here on top of this, cast in place slab. They'll start doing their columns and their pan deck. And then, hopefully by that time, this has reached its 28-day strength. And then they leapfrog up here. And then these forms will be pulled out. These flying forms will be pulled out, and they'll be shoved in here. If you're really interested in this, get on YouTube and just search concrete slabs with flying forms, and there will be some expert contractors that are proud to show you their work through their videos. All right. Now there's another type of construction called the lift slab. It's a technique of constructing multi-story buildings in which all horizontal slabs are cast at ground level, and they're cured. It's much like tilt wall, but it's tilt slab. It's not just jack slab. It's not tilt slab. You're not tilting the slabs. You don't see this a lot. You don't really see this a lot. All right. Now in silos, concrete silos or water towers, they'll use a very similar system, but it's called slip forming, where the concrete forms. You got this lower section poured, and then when that cures, they got the rebar going up. Then they'll jack these forms up, tie them in around the circle. This is a tube, okay? And then they'll pour the next section. And when that cures, they'll jack these forms up, and it's called slip forming. And sometimes we do it backwards, like for a lift station in the ground, for sewage to go in. You put pumps in. You'll come up here on the earth, and you'll pour your first box, your first wall for your box. Oh, that's pretty nasty. Okay, there it goes back like that. So you got this box, okay? And when this reaches minimum strength, there's usually a cutting foot on this because it's sitting on dirt. Then you'll come in here and you'll dig the dirt out from underneath it and let it sink. And this thing will sink into the ground. And then you'll pour another concrete box on top of it. Keep digging the dirt out and it'll start to sink, and pour another concrete box on top of it. It's called caisson, slip forming caisson concrete. I've got a huge lift station out at Southwest Wastewater Treatment Plant. That's how we did that. It was a round lift station. Had a big cutting edge underneath it. So it saves you from having to excavate, put retaining walls in, and then build it and then backfill it. All right, precast concrete floor systems continuing. Here we got precast. Now these would be precast and pre-stressed. Okay, when you go to, I don't know who the current companies are now. I know who they were back in my day, but the technology is the same. These cores are hollow to make them light. Your pre-stressing strands are in here. They cast hundreds of feet of these and they go and cut them at the length when the concrete's still semi-soft with concrete saws, and then lift them out. And they got tongue and grooves on the side, but these are precast and they're pre-stressed. All right, these are not post-tension. And what you do when you finish this, whether it's a roof or a floor, is you put light reinforcing steel in here, or steel fabric, depending on what your engineer wants, and then you pour concrete up here, and they'll go down. The concrete flows down through the grout key. You could specify these with tie joints. A lot of times what they'll do, here's an example, what they're doing here is they'll come in here and they will pour reinforced concrete in this cap to tie all this together. Okay, remember we talked about openings? Well, these are hanger bars. These are transfer structural members for an opening with these precast. These come out on a job. If you're ever out on a job, they'll be numbered and they'll be tied to the erection drawings, and you're just putting up a bunch of Legos. All right, let's see here. See this? See this poured tie cap? This is an end cap. So let's just presume this is a detail as if there's another column bay and beam bay, girder bay over here, and you're going to put some more of these over here. If it's an end run, then they'll cap it off like this. But here it's a span, okay? And in between here, we'll put reinforcing bars. And when we pour this floor, it'll pour down through here. Now, if this is an end cap run, we'd have to put forms out here, right? And they have pre-made forms that do that. All right, what's our time limit? What's our time? I'm gonna keep these about 45 or 50 minutes. I know you poor people are being talked to death, but hey, everything's in the book, right? It's a very detailed book. All right, so solid flat slabs, hollow core slabs, single T slabs. Now, why is it called a single T? Well, hey, Mr. Wizard, because there's just a T, one T. And these are double T's. Why? Because there's two of them. All right, wow. Isn't that cool? All right. And you thought us engineers were smart guys. That's just simple, right? Now, this was real popular to use these T's, these double T's, as walls. There was two mid-rise buildings over off of the 59 freeway back in the 70s and early 80s, and they may still be there. I don't know. I don't live in that area. Um, and the architect used these as the walls, and then he had holes precast in the flanges, and these would be sticking out, and for all the world to see. And then the window system would be either in holes in here or over here, or they'd space them. One of the buildings, if I remember correctly, was spaced, so there'd be a window wall system in here between a row of these, and then there'd be another one of these. So I know this isn't about walls, but we will get into walls later. Man, I think I need to use my pen instead of this. Yeah, let's see. Uh-oh. Let's see if this is any better. Oh, this is much more better. Mo better. Okay. And then this is the window. That's a window. And that's what the architect did all the way around the building. Okay. All right. I'm going to practice with that pen more. Now over here, again, are those nasty old rule of thumbs. Gives you an idea in your beginning phase what you can do. Okay? How you can span. And we're not talking about walls here for the height. Okay? So I went down a rabbit hole. All right? But these are general rules of thumb. Right? We've already talked about rules of thumb. Rectangular beams can be pre-stressed, precast, or they can be post-tension. I am not a big fan of post-tensioning. There's a lot of things can go wrong with post-tensioning. Now, there's some benefits to it, and the Post-Tensioning Institute will argue with me on that. Again, if it's a commercial structure and it's well engineered, it's well inspected, it's well managed, yes, you can get by with it. Safest thing, in my opinion, is pre-stressing, because it's manufactured in a plant and then it's trucked out to your site. And you can control what's going on in the plant, and you can do some preliminary testing, ultrasonic testing on those panels and beams before they get out, and you can catch the problems before it gets erected. All right, here's an L-shaped beam, and here's an inverted T-beam. Why is it called an inverted T? Because it's a T upside down. Oh my goodness. Here's an AASHTO. Okay, AASHTO stands for the American Association of State Highway and Transportation Officials. When you're doing highways and bridges and girders, you have got to go by the AASHTO codes. Okay, these were originally designed for highway bridges that put the deck up here. You probably have seen these if you've been around this area for any length of time when they were doing 99 around the Beltway and 249 and 290. They had these huge concrete beams on these trucks. And if you noticed them, what'd they have? They had a camphor in them. They had a camphor on them. They were bent up a little bit. Well, not like that, but okay. But they had a little bow in them going up. So when they laid them across and they started putting the road deck up there, these things flattened out. And they had construction engineers monitoring how much deflection to make sure that they deflected exactly the way they were supposed to. All right? This was all calculated by the structural engineers. All right? Again, here's a rule of thumb for those spans. All right, precast concrete connections. All right, these next couple of pages, where are we at? All right, we're almost 50 minutes. We'll go ahead and pick back up here. All right, this is going to be video 2. I said I was going to use my pen. Okay, I'm going to use my pen. Where's my pen at? There we go. All right, we're going to pick that up with video 2.